Hey everyone, today we're going to be going over acids and bases in the context of an OChem class. This will be mainly learning how to compare the acidity or basicity of two compounds without knowing the pKa or pKb values. To do this, we're going to be using the acronym ARIO, A-R-I-O. For a quick review, Lewis acids accept electron pairs, and we also call them electrophilic compounds. Lewis bases will donate electron pairs, and they are called nucleophilic compounds. In this example, we see that HCl receives an electron pair from H2O. Thus, HCl is our Lewis acid, since it's electrophilic, and H2O is our Lewis base, because it is nucleophilic. To compare acidity and basicity, we will be analyzing compounds in this specific order. We begin with formal charge and then follow the acronym ARIO, A-R-I-O. Regarding formal charge, a molecule with a higher formal charge will be more acidic. This is because a greater charge makes the molecule more likely to accept an electron pair, making it more electrophilic. Between H3O+ and H2O, the more acidic molecule is H3O+, because of the positive formal charge. Between NH3 and NH4+, NH4+ is more acidic due to its positive formal charge, making NH3 the more basic molecule. We now get into ARIO. The A stands for atom, and we are specifically looking at the size or electronegativity of the acidic or basic atom. If the two acidic or basic atoms that you are comparing are in the same row, the more electronegative atom will have greater acidity. The reason for this is the conjugate base. In the conjugate base, the atom contains a negative charge. The more electronegative atom will be more stable with the negative charge, making it a weaker base since it is less likely to react. Thus, its conjugate acid, the original molecule we were comparing, is a stronger acid. Let's work through this through an example. In our first example, we have HF versus H2O. So the atoms we are comparing is F versus O. F is more electronegative, so HF is a stronger acid from the principle we just talked about. Let's look at the conjugate bases to confirm this. The conjugate base for HF is F-, and the conjugate base for H2O is OH-. Now, F- is more stable because the F is more electronegative, so it holds that negative charge better than the O does. Since it is more stable, that means it is a weaker base, so HF is the stronger conjugate acid. That's why HF is a stronger acid than H2O. Now, if the acidic or basic atoms you are comparing are in the same column, the atom with the bigger radius will be more acidic. The reason for this is again due to the conjugate base. Atoms with a significantly bigger radius, meaning they have to be down a column, hold negative charges better, meaning they are more stable, even if they are less electronegative. Thus, the conjugate base is weaker because it is more stable, so its conjugate acid is stronger. Let's again work through this with an example. Between HBr and HI, I has the bigger radius than Br, so I is the stronger acid. Let's look at our conjugate bases to work through the logic once again. So the conjugate base of HBr is Br-, and the conjugate base of HI is I-. Now, I has a bigger radius, so it is more stable. More stable means it's a weaker base. And since it's a weaker base compared to Br-, HI is the stronger conjugate acid. Thus, it is a stronger acidic molecule. Based on the acronym ARIO, the next thing we look at is R resonance. If a molecule's conjugate base has greater resonance, the molecule is a stronger acid. This is because resonance will stabilize a negative charge, so a conjugate base with greater resonance will be more stable and a weaker base. A weaker base will have a stronger conjugate acid. Let's look at our first example. This is the conjugate base for the first molecule, and this is the conjugate base for the second molecule. Now, only the conjugate base for the second molecule has resonance, as shown below. This means that this conjugate base is more stable because of its resonance, meaning it's a weaker conjugate base. So, this molecule is the stronger acid. Let's look at our second example and draw out the conjugate bases again. I'm only going to draw one example of a resonance structure, but there are multiple others which do stabilize that negative charge. So again, this conjugate base is more stable, meaning it's a weaker base. So this molecule is the stronger acid. Following our acronym, the I stands for the inductive effect, which is the result of electronegative atoms. The greater the number of these electronegative atoms and the closer they are to the acidic hydrogen, the more acidic the molecule. The reason it makes the molecule more acidic is because it stabilizes the conjugate base, drawing some of that negative charge towards it. Those electronegative atoms have a negative inductive effect, and that stabilizes the molecule, the conjugate base. A more stable conjugate base is again weaker, so its conjugate acid is stronger. For the first pair, the Cl is closer to our acidic hydrogen on the first molecule. On the second, our Cl is all the way on the other side. Thus, the first molecule is more acidic. For the second pair, the electronegative atoms are in the same position relative to the acidic hydrogen. However, the F is more electronegative than the Cl, so this molecule is more acidic. Lastly, the O stands for orbital. To analyze this, you have to look at the acidic or basic atom in your molecule. The greater the S character of this atom, the more acidic it is. To find the S character, you have to look at the hybridization. A molecule that is the atom that is sp hybridized will have the greatest S character, and the atom that is sp3 hybridized will have the least S character. So, let's look at it for these three molecules below. If you remember, you would already be able to tell this molecule is the most acidic simply based on formal charge. But let's also go through and find the S character, the hybridization for each of them. This nitrogen has 4 electron groups, it is sp3. This nitrogen has 3 electron groups, it is sp2. And this nitrogen has 2 electron groups, it is sp. So this has the greatest S character. This is in the middle, and this is the least. So this, again, supports that the molecule on our right is the most acidic molecule. I'll rank that with a 1. The middle molecule, that's sp2 hybridized on the nitrogen, is the second most acidic, And the molecule on the left, which is sp3 hybridized for the nitrogen, has the least S character, so is the least acidic. Thank you so much for listening.